Yeah, good afternoon to all. So the second session of the second week of the workshop on data assimilation for weather and climate, the presentation will be made by Dr. Indira Rani, Senior Scientist at National Center for Medium Range Weather Forecast, Delhi. So Dr. Indira Rani does research in satellite data assimilation, reanalysis and numerical weather prediction. These are her major areas. So she's a senior scientist and she has done her PhD from Space Physics Lab in 2009 in mesoscale modeling, I would presume. And then today's Dr. Indira Rani will be speaking on overview of data assimilation and operational forecast of NCMRWF. I request Dr. Indira Rani to take over. Thank you.
So, thank you, sir, for your kind introduction. And I would thank Fiona also for setting the stage for this presentation, because if you see the operational centers, the usage of data or the data assimilation method, everything, it is almost similar. So you may find some repetition in this presentation also. So I think that is good if you get the same thing repeated, that you get more understanding about those kind of thing. So today I'm going to give an overview of data assimilation at NCMRWF. It is NCMRWF, it stands for National Center for Medium Range Weather Forecasting, and it is a center, subordinate office under the Ministry of Earth Sciences. So if you see the operational centers, we do use more data. That in the first week you have seen lot of theory on data assimilation. So in this presentation I am not going to touch any of the theory part, because you are better known for that theory, all those things, and what are the different types of data assimilation techniques, whether it is variational assimilation technique, whether it is ensemble methods. You have some overview of that those methods. So in this one, the outline I'm planning to give that NCMRWF assimilation systems, because if you see, NCMRWF is the data assimilation center for the sister organizations of Ministry of Earth Sciences and other government and private institutions. So we do the data assimilation for IITM, IMD, INCOIS. INCOIS, they are running the ocean model, so they need the flex, atmospheric flex, for forcing their ocean models. So those initial conditions are provided by NCMRWF. And the observation reception, as you know, the data assimilation means the main important thing is the algorithm is the important thing. Then algorithm, once it is developed, so it is fixed, and then we need the different types of data. So what are the different types of data that we are receiving at NCMRWF? And this data, again, Fiona already told that in situ and remote sensing. So similarly, conventional observation and the satellite based observation, all those things. And I just would touch upon the Indian satellite data. So you know, we have so many Indian that meteorological satellite missions. So how do we use all these data at NCMRWF? And to name a few, that the Megatropics, Microsat 2B, INSAT 3 series and OceanSat series of data. And what are the observation gap areas? So as I already mentioned, that we are the operational that assimilation center for Ministry of Earth Sciences. So we do run the assimilation for two global models. One is the NSUB based GFS system, and another one is the UK Met Office based unified modeling system. So the NSUB GFS system, that is the IMD's forecast model, is the GFS based system, but IMD means consider all the model, not only the GFS system, they consider the NCM, that is the NCMRWF unified modeling system. Then they consider the JMA, ECMW. So their forecast is not based on a single model, but they consider multiple models. So if you see the data assimilation for these two systems, it is complex, it is not that simple. So we have in both the system, we use the hybrid data assimilation. So I think you know what is hybrid data assimilation. Do you know what is hybrid data assimilation? So actually we mix two type of data assimilation here. One is the variational data assimilation and another is the ensemble data assimilation. So at our center we run two global system, like based on both the system. One is the ensemble system, one is the deterministic system. So the deterministic system is running at 4D-var data assimilation for the unified model, and for the GFS it is the grid statistical interpolation 3D-var based. And both the system that we have the ensemble system also. So the hybrid system, in the hybrid system we give that the weightage from the ensemble system also. So currently we are giving 30% the climatological background error covariance and 70%, sorry, 30% from the ensemble and 70% from the climatology. So that's why it is called the hybrid data assimilation system. So both the system, both GFS based system and the UM based system that we are running at NCMRWF is hybrid. Hybrid in the sense we use the background error covariance from the ensemble system also. So that is why we call hybrid. And if you come here, that the unified modeling system, whatever we are running at NCMRWF, it is the seamless prediction system. So what is seamless prediction system? By seamless prediction system, we mean it is the same dynamical core of the model. So we are not using different dynamical model for running the different types of model like global, ensemble, regional. Then we have the 330-meter Delhi fog model. So for all these type of models, whether it is global model or regional model or it is urban scale model, we use the same dynamical model. So the dynamical core of the model is same. That's why we call the unified modeling system as the seamless prediction system. So that means we don't have to compile the model for running the regional separately, that urban model separately. So the same compiled code we can use for all different types of model with different horizontal resolution. So if you see, we have the global deterministic system which is running at 12-kilometer resolution. So by 12-kilometer resolution, you know what is the grid space, that the horizontal grid spacing is 12 kilometer. And we have the global ensemble prediction system that is also of the same resolution of the global deterministic system, that is again 12 kilometer. And at each cycle we run 23 members and 10-day forecast. From the 12-kilometer model also we give 10-day forecast. And we have the 4-kilometer regional model that is over the Indian region. So from the 4-kilometer regional model we give three-day forecast based on the 0 UTC initial condition. And apart from that we have 1.5-kilometer regional model that is also that covering the Indian region, but this model we run only during winter for the 330-meter Delhi fog model. So you know that during winter that Delhi, the fog condition, pollution, that is very worse. So then in that during that period we run the Delhi fog model. With that, for the lateral boundary condition and the initial condition, we run a very high resolution regional model of 1.5 kilometer resolution apart from the 4 kilometer. So this is the seamless prediction system at NCMRWF. And these are some of the configurations what we are using. So for the this is already I have shown here in this figure, but again this is in the tabular form, that is the urban model and mesoscale model 1.5 kilometer. Then we have the 4 kilometer model also, global NCUM, that is the global system, then the ensemble system, and we have a coupled system also. Coupled system we are running at a coarse resolution. Whatever is operational now, the horizontal resolution of atmospheric model, atmosphere part is 60 kilometer and the ocean is 25 kilometer, but it is compared to the 12 kilometer deterministic, the atmosphere part, atmosphere model in the coupled system is very coarse, it is 60 kilometer. But now we have tested one coupled model with 10 kilometer resolution also, but it is not yet operational. So in the new HPC, we implement the coupled system also. So then the coupled system with 10 kilometer atmosphere and 25 kilometer ocean, that's what we are planning. So then in that case, our deterministic system we will close, because the coupled system we will use for the NWP forecast also. So this is again that GFS based system. So we have the HRRR, that the high resolution rapid research model version of the WRF system. Then we have the HWRF, then the global spectral model, that is the IMD GFS, that 12 kilometer resolution, and we have the ensemble for that also. So both this model, the data assimilation has been run at NCMRWF, and we do the data assimilation and transfer the initial condition to the corresponding agencies. So this is the meteorological and oceanographic observation data that we receive at NCMRWF. So you know that for we are running 2 global models, so we need all the global observations. So how do we get all these global observation and in near real time, because we are running the operational model, so we have to get the data at near real time. So at NCMRWF we get the data from different sources. So the main source is the GTS. GTS stands for Global Telecommunication System. So this is the WMO, the Global Telecommunication System from all over the globe, basically all the conventional observation that is transmitted through the GTS. And we have MOU with NOVA, UMedcast. So these are the satellite data providers. So we get almost the NOVA satellite, that the US satellite and the European satellite. So through NOVA and UMedcast, and from IMD and ISRO. So if you see that inside 3D and inside 3D are imager, sounder and the GNSS IPW. So Fiona already explained what is the GNSS RO, GNSS Zenith total delay, all those things. So those data from the Indian region we are getting through IMD. And from ISRO, so ISRO senders, they are having the DBNet station, that is the direct broadcast network stations. So those data and the OceanSat and the Microsat 2B data that we are getting through ISRO. And other data set like some of the QSAT wind profiler we are getting from QSAT, then some Navy wind profiler, and some other data we are getting from other sources also, because the CMA, the Chinese satellite data we are getting through CMA cast, and the Korean satellite data we are getting through KMA cast, like that. So if you see that at NCMRWF we receive almost all the global data in near real time. And if you see the GTS data, it is mainly the conventional data, surface, upper air, satellite winds. Satellite winds, it is not conventional, but some of the satellite data also we get through GTS, and some of the radiances also we get through GTS and the GNSS RO, the radio occultation data. And if you see the NOVA, so almost all the NOVA satellite data, so we get through the NOVA that we have the NKN connection with the NOVA POD, so that we get all the data through that service. And apart from the satellite radiances, we get some of the satellite winds, that polar winds and the GOES 16 and 18, that is over the GOES west and east, that satellite. And other satellite observations like ozone and GPSRO, that is the commercial GPSRO data. IMD has an MOU with NOVA. So NCMRWF is the data assimilation sender for IMD. So that data directly we are getting at NCMRWF, but we are not supposed to share this data immediately. So we can share this data only after 24 hours, because it is particularly this GPSRO spy data, because it is the commercial data. So similarly from the UMedcast, if you see, we are getting almost all the satellite radiances, then the DBNet service, satellite winds, those things we are getting through UMedcast, almost all the European satellite data. So we are on par with other operational centers like ICMWF, Meteo France, BOM, NSEP, like that. We are getting almost all the data in near real time. So if you see that the WMO regional associations, so since we have to get the data from all over the globe, the WMO has divided the whole globe into different regional associations. So these are the different regional associations. So if you see, there are some 6 that regional associations, and we are in the second, the region 2. So Asia, this is coming in the second RA2 region. And how do we get the data? That we were talking about the GTS, that is the Global Telecommunication System. So this is the Global Telecommunication System. Then you can see that India is here, and we have the World Meteorological Center. Three main centers are there. That is, one is at Washington, then Moscow and Melbourne. So these are the main 3 centers, and we have another regional telecommunication hub also. This is just to show the network, how the data is transmitting through the GTS. So at New Delhi, that we have one regional telecommunication hub. So almost all the global data, it is coming to the RTH Delhi, and from RTH Delhi it is immediately transmitting to the NCMRW. So we are getting every 15 minutes we are getting the data from RTH Delhi. So if you see, this is the GTS network in India. So you can see there are many regional meteorological centers, and that it is connected to the RTH Delhi. From RTH Delhi also the data is going to different regions, like to more different parts of the world. So like this, that all the global data, it is shared among all the operational centers. So these are the different types of observation we are assimilating. So this, like surface, we are getting through GTS, and surface means it contains the SYNOP data, ship, buoy data, then METAR, TC bogus, AWS data, like that. And upper air, it is the pilot, that pilot observation means the pilot winds, it is the profiles, then radio sonde, then we have the wind profiler, drop sonde, Indian DWR, wide winds, reflectivity, radial wind, all those things. Then we have the satellite winds, and this the red color, it shows these data we recently added in our operational system. Like inside 3D it was already there, and 3DR imager and imager sounder and the AMVs we recently added, and GOES 18 also we added recently, and dual metop winds that we added recently, and OSCAT 3, that is the OceanSat 3 satellite, that is the latest scatometer mission by ISRO, that also we did. Now it is operationally assimilating. And inside 3D sounder, and this is the radiance part inside 3D sounder and GOES 18 ABI radiances. And coming to the microwave part, that microsat 2B, that is the EOS 7, that is the Earth observing satellite. So now ISRO, they are naming the satellite as Earth observing satellite. So EOS 7 is the latest experimental satellite launched by ISRO, and we have the data access from ISRO, and we are assimilating this data also. And coming to the GPS RO, she already explained how that radio occultation, bending angle, refractivity, those things we are measuring. So those data also we are getting mainly through GTS and some through NOVA and UMedcast. So these are the different types of data we are receiving. And now we will see the data in detail. So coming to the surface data. So if you see, this is the global, she already shown this type, this plot, that if you see that for BOM and for NCMRWF, for any of the operational center, this type of plots are almost similar, because almost all this data we are getting through GTS. So here you can see that we are getting different types of observation in near real time. So land SYNOP, SYNOP means it is the surface observation. SYNOP is a WMO code, that's why it is called land SYNOP. And we have the ship observation, you can see that color, that green color. And we are getting this WMO data, whatever they are transmitting through GTS, that is a coded data. So we suppose if we are measuring the temperature at Delhi or Bangalore, and if we are reporting the temperature in some local language, and if we are transmitting that through GTS, so the people in US or in Europe, they cannot understand the language. So there should be a unified code to transmit the data. So WMO has developed some code, that is the traditional ASCII code, that is called TAC. And there is buffer code. Buffer also, it is a binary code, it is a table driven code for transmitting the GTS data. So we are getting the data in different code also, that's why here you are seeing that ship buffer like that, sorry, ship buffer, it is coming in buffer format. So you can see that almost all except if you see the northern hemisphere, we have almost all the data. But there is lot of gap in the southern hemisphere, because you see that southern hemisphere, it is majorly the ocean, the land part is very less, but compared to the northern hemisphere. But we have still we have lot more buoy observation, ship observation over the southern hemisphere also. And we do the quality control and monitoring of the Indian data. So if you see the SYNOP data over India, so this is the SYNOP observation over India. So this one, so actually at NCMRWF, we do the data assimilation at 6-hourly interval. So we have 4 assimilation cycle centered at 0 UTC, 6 UTC, 12 UTC and 18 UTC. So each 6-hour interval, we use the observation from plus or minus 3 hours. So centered at 0 UTC, the previous day 21 UTC to current day 3 UTC. So we have the 6-hour assimilation window. Similarly for other cycles also. So this is for a particular assimilation cycle, and if you see for that particular assimilation cycle, within that 6 hour, that plus or minus 3 hour centered around that assimilation window, we received this many SYNOP observation over India. So we have this, again this is not 298 SYNOP, we don't have 298 SYNOP station, but this is hourly observations. Again, we have the AWS observation. This is the total network over India. So this is only the reception. Then we have to do the quality control. Then we don't assimilate all this data. So in the quality control procedure, that we may reject many of the data because of many reasons. So this is again the buoy observation over India. Mainly if you see this green and this blue, that these buoys are operated either by INGOIS or NIOT. These are Indian buoys. So these data also we are assimilating in our system. So here these two colors, it is coming in two format, one in ASCII and one in buffer. That's why it is on the same observation, but we are receiving in two different format. So this is the surface, and if you see the upper air, so this also she showed that same similar plots. So you can see the upper air data. So we have a good network of upper air data over the Indian region. So we have around, actually if you see that installed radio sonde station means there are around 60 plus radio sonde station, but right now we are getting around 40, means 40 stations are operational. So 40 radio sonde observations we are receiving over India, and along with that pilot wind profile also. So we don't have any the wind profiler data over the Indian region, except like QSAT we have the data, but that data we are not getting through GTS, that separately we are getting. So this is the upper air network, and here also we do the monitoring and quality control of the Indian upper air network. So here in this particular cycle we received the 37 radio sonde data. So here one important thing that we noticed is when IMD sends the data, so they are sending the radio sonde report. Radio sonde report means it contains temperature, humidity and wind profiles. Means profile means atmospheric, the different levels of the atmosphere you have the information. And along with that they extract the wind profile separately and they send that as the pilot observation. So these are the same, almost the same location, but it is sort of duplicate reports. It's not that separate pilot wind and radio sonde observations. So then we do the analysis, how much height the radio sonde has gone. So we have to see whether it has the balloon has burst after reaching maybe like 500 HPA or 200 HPA or at the surface, that we have to see. So that we do the analysis at what height it has reached. So that type of monitoring also we do. And we do how much data we have assimilated in our system. So this one, if you see that, you know that radio sonde observation all over the globe, we do the measurements at 0 UTC and 12 UTC for the uniformity. So 0 UTC means in Indian local time it is 5:30. So morning 5:30 we IMD does the radio sonde measurements, and evening 12 UTC means evening 5:30. So if you see that morning observation, we are getting more observation compared to the evening observation. So it is due to the lack of manpower and all, they are not making that much radio sonde measurements during 12 UTC. But here you can see that during the COVID time, there is a drastic decrease in the number of radio sonde. So this time that we were, IMD was not having the radio sonde payload, and there were lack of manpower also. So that time we witnessed a very huge, very drastic reduction in the number of radio sonde that we received over the Indian region. And if you see this blue bars are the monthly average count, how many radio sonde we are receiving, and this red line is the percentage rejection. So if you see that the percentage rejection in the atmospheric, that our model is very less, it is around maybe 1% kind of thing. But most recently what we saw, the rejection percentage of the Indian radio sonde data, it is slightly increased, and we investigated what could be the reason for that. It is because of the radio sonde type. So the whatever the radio sonde type it is coming, that is not of good quality. That's why the data assimilation system is rejecting many of the data. This is not for all station, but some station, some particular station, the radio sonde is not of good quality, and the rejection is very high percentage. Similarly, you can see that 12 UTC also, the rejection percentage is around 3% kind of thing. Okay, so then comes the aircraft observation. So this also she showed that aircraft observation. So whatever we are getting, that it is wherever there is high that air traffic region, we have the more observation. And if you see over the Indian region, so here it is written Arab, Amdar, Vigo, Samdar. So these are some type of aircraft observation. So Arab means it is the pilot observation. So the pilots makes that what is the temperature, pressure, or wind, or humidity, and humidity at that level. So then they send it whether sometimes it is automatic and sometimes it is manual. So these observations are sent, and Amdar it is automatic relay observation. And Vigo Samdar means it is some WMO region, they have that sort of that Amdar particular, if you see this US region, they have the WMO particular observation region, and that's why it is called Vigos. So if you see over the Indian region, we were getting very less observation, and we conducted through IMD, because the observation that all observation agency that are maintained by the IMD, and we through IMD we contacted the Airport Authority of India and Ministry of Civil Aviation, and we started getting more data. That mainly it is from Delhi, then from Mumbai, Kolkata, Chennai. So we started receiving more data, and since then that if you see the number of observation over this particular domain, that is mainly 20 degrees south to 40 degree north and 50 degrees to 120 degree east, that we started getting more than double the data. And if you see the aircraft observation, mainly the aircraft observation, it is confined in the upper level. So why it is so? So most of the takeoff data and landing data we are not getting. So if we get the takeoff data and landing data, these observations are similar to radio sonde. So much more information is there in that data. But those observation we are not getting through GTS. But mainly if you see that above 300 HPA, most of the observations are confined above 300 HPA. So then we did some OSC. OSC means observing system experiment. So we have the data, what is the impact of that data in the assimilation system. So this is again during COVID time. If you see that there is a decrease in the data, and slightly, if you can see slightly, it is means changing, that it is moving back to the pre-COVID period. So we did the comparison with the ECMWF, how much data they are receiving. So here also you can see that COVID-19 impact, at that time the data reception at almost all the operational centers, it was very less. And if you see that this is an example, so this is 2019, 10th April, so we have lot of observation, and this is the same thing 10th April 2020, so during the COVID period. So you can see the number of observation, here the numbers are written, even though it is there, but the numbers are very less, and if you see over the Indian region, the numbers are very less. So we did one OSC, what is the impact of this observation in our system. So this is the analysis increment plots. Analysis increment means we do the assimilation, and we see, actually we are running the 4D-var incremental analysis system, assimilation system. So in that we get the analysis increment of different variables. So here you can see the specific humidity, then the potential temperature and the zonal wind. So here if you see when we assimilated the aircraft data, as we already discussed that most of the aircraft data, whatever we are receiving at NCMRWF, it is confined at above 300 HPA. So what we saw, the impact is mainly above that higher levels. So even in the specific humidity, potential temperature, even though we can see some impact in the lower levels in the specific humidity, but if you see mainly the impact is confined over the upper atmosphere. So it is mainly over the higher altitudes, even if we could see some impact in the lower atmosphere in the specific humidity. So then we did this one, how this the monsoon features like low level jet and TEJ, how it is affecting. So we can see that at first glance there is not much change in the LLJ and TEJ. So this is with aircraft data and this is without aircraft data. But if we see the differences in the low level jet, we didn't see much impact because most of the data it is confined over the upper atmosphere. But if you see in the upper level, the TEJ, we could see a lot of impact due to the assimilation. So here this is the aircraft data region. So here you can see a lot of impact over those regions due to the assimilation. So this mainly it is we noticed it is relatively heavy air traffic area. So where we are having more aircraft observation, there the impact was more. Here again the TEJ and LLJ you can see. LLJ again we didn't see much impact in the assimilation, So, but the TEJ, if you see the difference, this is with and without, but this one it is not showing much difference. If you see the difference between these two, you can see we are getting a maximum of 3 meter per second. So, in the TEJ, when we assimilate the aircraft observation, we got strong TEJ in the model. Again, similar to the impact in the assimilation of that simulation of cyclones. So we didn't see any impact during the initial stage. So if you see this we did with our reanalysis, that's why it is coming as IMDA. So data denial, if you see the data denial means initially there was some impact, but after that it is some change or something like that it is coming. But if you see in the mature stage, if you see that whatever that we assimilated the aircraft, so IMDA means it is with aircraft, and the data denial there is no aircraft like that. So here we can see that in the mature stage of the cyclone we could see the more impact of aircraft data, because if you see in the mature stage the divergence, the upper air divergence are coming into play, and that data it is affecting the system. But in the initial stage or the low depression, that time we didn't see any impact. Okay, so then she also, Fiona already explained why do we need the satellite data. So these are the conventional data. So the limitations of conventional data are mainly, if you see the upper air data, it is mainly confined over the northern hemisphere, and we don't have much observation over the southern hemisphere and over the ocean. And if you see the surface observation, we have almost all the global coverage of surface observation. But again, it is what is surface observation? It is single level observation. We don't have the information above that one. So even if we have information from the upper air observation, we have the information above the atmosphere at different multiple pressure levels, but it is very much confined over land, and it is over the northern hemisphere. But this one, the limitation is it is limited to the surface level only. So we need for the data sparse region and the remote region and over the ocean, we need more data. So you may be knowing that what are the different types of orbits what we are using in the data assimilation. So we have the polar orbit, and we have the geostationary orbit. And polar orbit, it is usually from maybe we can say like 850 kilometer that orbit height from the Earth's surface. And for the geostationary, it is 36,000 kilometer. And we have inclined orbit. So inclined orbit means the polar orbit, the inclination is around 90 degree, but for the inclined orbit, the inclination angle with respect to the equator, it is not 90 degree. So we can change that one. So one example is the Megatropics. Megatropics is a low Earth orbiting inclined satellite. So the inclination was around 20 degree. So that means if the inclination changes, the coverage area also changes. So where we want to probe the atmosphere more, likely we can change the inclination also. So another one is the highly elliptical orbit. So that if you see the geostationary satellite with respect to Earth, it is stationary at a particular location. So where the satellite is, it seems to be stationary because the period is around similar to the rotation of Earth. So in that case, we can probe the atmosphere maybe in the tropics and extra tropics continuously. But if we go to the polar region, we don't have the continuous observation. So in order to get the continuous observation over the polar region, we use the elliptical orbit. So if you see where you want to see the atmosphere more, so here the orbit is more, orbit height is more over this northern pole region. So here that satellite station more time over that region. So the satellite sees that location continuously for long time, and we get more information. It is sort of geostationary in the polar region. Similarly, if you want to probe the southern hemisphere, we can change that the elliptical orbit where it has to, means like the perigee and apogee we have to change. And another thing is the medium Earth orbit. So medium Earth orbit, it is all the GNSS satellite, that is the Global Navigation System satellite. They are in the medium Earth orbit. So we say that the polar orbit, it is at 850 kilometer, and the geostationary at 36,000 kilometer, and the medium earth orbit. Medium earth orbit plane you can change, whatever plane you want that you can change depending on your constellation. And medium earth orbit, it is at 20,000 kilometers. So it is in between polar and geostationary. So mainly the medium earth orbit, all the GNSS satellites are there. So the radio occultation, the constellation, that satellite, GNSS satellites are in the medium earth orbit. So this again, she showed all these things, but still I'm just showing over the Indian region. If you see, there are many satellites looking over the India and the surrounding region. So we have the Himawari. Himawari is the Japanese satellite, and we have the GeoComSat, this is the Korean satellite, and we have F54, that is the Chinese geostationary satellite, and we have our INSAT. And Chinese satellite, there are two satellites are there, then INSAT 3D and INSAT 3DR. Now we have the INSAT 3DS also. And there is another geostationary satellite, that is by Russia, Electro L. So these, if you see the Indian Ocean region, there are many satellites. So main study that all are looking at the Indian Ocean region. And apart from that, if you see, there is another satellite by the European Space Agency, Meteosat. So that is also over the Indian Ocean region. And here we have the Meteosat third generation one, that is over the Africa and European region. And we have the GOES East and GOES West for the European, means US region. So this is the geostationary coverage. And you can see the polar satellite, there are many polar satellites. So as she already told, that polar satellite, it rotates Earth in a faster rate compared to the geostationary. So in order to get a complete the coverage of the data, we need some time. Basically 14 days we take to get the complete observation over Earth. So then we need multiple polar satellite to get the complete coverage. So there are multiple polar satellites. So these are some examples. If you see METOP is the European satellite, and FI3 is the Chinese polar satellite. So Chinese satellite, this even series are geostationary and odd series are polar. So FI4 is the geostationary and FI3 is the polar satellite. And TRIM, it is not there now, but instead that we have the GPM, and we have all the afternoon train, 8 train satellites in the polar orbit also. So then these are some of the main satellites that satellite instrument we are using at NCMRWF. So she already mentioned almost all these instruments, but if you want I can explain, otherwise I can skip. So this actually, I don't know if you want. Okay. So that ETOS is a group of 3 instruments. So ETOS means it is stand for Advanced TIROS Operational Vertical Sounder. So we have this instrument in different satellite, like NOVA series of satellite and European METOP series of satellite also. So the 3 instruments in ETOS are HIRS, that is the High Resolution Infrared Sounder. It is an infrared instrument. And we have AMSU-A, Advanced Microwave Sounding Unit A. This is for temperature channels. And AMSU-B or MHS, that is the humidity channel, microwave humidity sounder. So these 3 units constitute ETOS. So ETOS is a group of 3 instruments and it is in the microwave. So if you see the multispectral LEO, so these are in the multispectral. Multispectral means the number of channels are countable, that is maybe less than 25 kind of thing. So then we have the AMSR2, that is the Advanced Microwave Scanning Radiometer on board GCOM-W1. This is the satellite by Japan. So this is AMSR2 is an imager, and ETOS, if you see, it is a sounder. So there are differences between sounder and imager. And ATMS, again, it is Advanced Technology Microwave Sounder. So it is like we have ATMS instrument on board 3 satellites now. One is the SNPP, another one is the NOVA 20. Now in the latest satellite NOVA 21 also we have the ATMS. ATMS is Advanced Technology Microwave Sounder. And the SSMIS, that is the Special Sensor Microwave Imager Sounder on board DMSP, that is the Defense Meteorological Satellite Program by US. So this also we have many satellites, that F series, F17, F18, F19. And the another one is the GMI, Global Precipitation Mission, GPM microwave imager. So these things, if you see, these are in the multispectral LEO, that the channels, if you see, these are limited. So ETOS, if you consider HIRS is a 20 channel sounder in the IR and visible region. So there are 19 channels in the IR region and 1 channel in the visible. And AMSU-A, it is a 15 channel microwave sounder for the temperature soundings, and AMSU-B or MHS is a 5 channel humidity sounder. So if you consider all these things together, there are 40 channels, 20 in HIRS, 15 in AMSU-A and 5 in MHS. And AMSR2 also we have some 14 channels, and ATMS we have 22 channels. Like that, there are multispectral, limited number of channels in this instrument. Then comes the hyperspectral. Hyperspectral, she already explained that hyperspectral. So it is numerous channels, it is like thousands of channels. So if you see ERC, ERC stand for infrared atmospheric sounding unit. So again, all the hyperspectral instrument right now we are having, it is in the infrared region of the spectrum. So we have ERC onboard METOP series of satellite. Right now there are 2 satellites, METOP B and METOP C, and there was METOP A, so that is not operational now. And AIRS, it is atmospheric infrared sounder onboard Aqua satellite, and CRIS is cross track infrared sounder onboard SNPP and Nova 20. So you can see that we have the microwave sounder ATMS onboard SNPP, Nova 20 and Nova 21. Similarly, we have the cross track infrared sounder in the same satellite in SNPP, Nova 20 and Nova 21. And if you see the ETOS we are having in the METOP series of satellite, and we have ERC, the hyperspectral, also in the METOP series of satellite. So the same satellite carries many payloads. It is not like one payload, but there are many payloads like hyperspectral, multispectral, then the scatterometer, multiple payloads will be there. So if you see the coverage of the data, so this is the coverage of the satellite radiances from the multispectral and the hyperspectral data that we are receiving at NCMRWF. So you know the equator crossing time will be different. Depending on the equator crossing time, the data coverage also different. So that's why you are seeing some gap here. So this is for particular assimilation cycle. So in the next cycle or in the next to next cycle, that coverage, it is the pass is over Indian region also. So here you can see that depending on the satellite, which satellite it is, and depending on the equator crossing time, we are getting the full that global coverage from the polar satellites. So then comes the radiances from geostationary. So we have around insert 3D-R imager, 3D and 3D-R imager and sounder data. So right now we have 4 instruments, but unfortunately the sounder on board insert 3D is not working. So 3 instruments, insert 3D imager, insert 3D-R sounder and imager. And we have the SEVIRI, that is spinning enhanced visible and infrared imager on board Meteosat series of satellites. So right now 2 Meteosat satellites are operational, and we have the SEVIRI data from 2 satellites, one over the Indian Ocean region, that is the IODC coverage area, and one over Africa and Europe region. And AHI, it is the advanced Himawari imager on board the Himawari satellite, and ABA is the advanced baseline imager on board GOES satellites. So if you see the coverage, so this is she already showed that this is the full geostationary radiance data coverage what we are getting at NCMRW. So this is the insert 3D and 3DR. So it is not included here, but separately we are plotting this data for insert 3D and 3DR. So if you see between 70° north to 70° south, we have almost all the coverage from the geostationary data, radiance data. So then comes the satellite winds. So she already explained how that we are measuring all these satellite winds. So I am not going to the measurement techniques, but from how many satellites we are getting all these data. So again, geostationary data we are getting from insert 3D and AMVs from insert 3D and 3DR, Meteosat 9, 10, Himawari, almost all these the geostationary data, whichever that instrument is having the imager. So all from that imager we are deriving the AMVs. So this in addition to the geostationary, we are getting the AMVs from the polar satellite also, and the dual METOP winds also. So this is the coverage. If you see, we are getting the full global coverage of all the satellite AMVs. So you can see here, this is the insert 3D and 3DR coverage. If you see these 2 green shades, But compared to other satellites, we are not getting the full disk coverage from these two satellites. This is due to some navigation issue, and ISRO is working on that. In the latest INSAT 3DS, they are planning to remove some of the navigation issue. That's why we are getting the sector generated product over from the INSAT 3D and 3DR AMVs. So then if you see that polar region, we have seen in the previous slide that coverage is between 70° north to 70° south, but we have the AMVs from the polar region also. So that is from the polar satellite. So polar satellite, how that continuous images are coming, so then they are tracking the tracer in that particular, whether it is cloud or water vapor. So they are tracking, and accordingly they are deriving the winds. And if you see, we have some that like some polar orbit tracks also. This is from dual METOP wind. So if you see the METOP satellite, so their equator crossing time is only half an hour difference. So we get the continuous image from two satellites. So then we can track the same feature in the images from the two satellites, and we can derive the AMV. That's why we are getting the dual METOP winds. Okay, then again satellite winds, we have the scatterometer. So scatterometer, right now we have three scatterometers, ASCAT B, ASCAT C and OceanSat 3. So here you can see that the scatterometer winds we are getting at 6 and 18 UTC. So 0 and 12 UTC, we don't have any scatterometer coverage over the Indian Ocean region. So this is at 6 UTC, this is at 18 UTC. So other cycles, if you see, we don't have these. So that is one of the data gap in the assimilation area. So we should get that scatterometer coverage from the early morning or that early afternoon orbit also. So then another thing is the wind. Actually, when we talk about winds, that AMVs, we are telling that cloud, that motion vectors, that again it is at a particular level. It's not profile kind of thing. And scatterometer, it is only over the ocean, and it is again a 10-meter wind. And if you want the atmospheric wind profiler, so wind, if you see the tropics, the winds are more important than radiances or the brightness temperature. So if we assimilate more wind over the tropic, that our forecast, that's what we found in our OSC and from other researchers that reported study also. So there is one instrument that is the space-bound wind lidar. This is the Aeolus Doppler wind lidar, DWL, Doppler wind lidar. So it measures the data. Actually, whatever the data we are getting from this Aeolus satellite, it was like we tell that it is HLOS, that is the horizontal line of sight wind. So it is not the full vector. So full vector wind means we have the U component and V component, but from this satellite whatever we receive is only the horizontal line of sight wind component. So the measurement techniques, if you see, so they do the measurements in two channels. One is the Me channel and one is the Raleigh. This is again depending on the scattering. So Me scattering and Raleigh scattering. So Me, it is from 0 to 16 kilometer, and Raleigh we get up from 0 to maybe 30 kilometer kind of thing. So then whatever that continuous coverage along track data, and it is again the wind profile. If you see that we get the wind profile from surface to, depending on the channel, we get the wind profiler from the surface to 16 kilometer or surface to 30 kilometer, what we are using. So then this is again mostly zonal component of wind, because if you go towards pole, we get more and more meridional component, but if you see over the tropics, it is mostly zonal component of wind. And this is again the measurement technique. So this is what we get from the Aeolus satellite. So this is the 1 day coverage. So these are all the wind profilers that we are getting the wind profile, means wind observation at different level. So then we analyzed how these winds are representing our monsoon circulation. So TEJ and the low level jet and the low level jet and the TEJ. So we found that these things are well represented in this type of observation, and we did some assimilation of this data during some cyclone cases also. So this is one case of that cyclone Totke, And if you see that after the quality control, how much me cloud wind we assimilated this only this much. So the quality control procedure that it rejected most of the data, and assimilated Raleigh clear winds also it is this much, but still we got some impact in the assimilation system. So these type of observations are very important in the assimilation, particularly over the tropics. So then what is the complementarity between this Aeolus wind profile and the radio sonde thing? So we did the collocation of the Aeolus wind profile and the radio sonde over the Indian region. And if you see, this is the zonal wind and meridional wind component, and as we already explained that Aeolus is providing the mainly the horizontal component of wind. So if you see the zonal wind profile, the Aeolus that profile also it is almost matching. So then that means whatever the assimilation we have did, we found that there is a good complementarity between the radio sonde wind and the Aeolus wind profiles. So this is another important the data that we use, but unfortunately this mission it has stopped, and it was live only for 2 to 2.5 years, because it is an active system. So that lot of power is required, and it's very difficult to maintain the system. That's why that now it is not operational. And ESA is planning for the next that repeat also, but I don't know when the repeat will come. So this the next one, GPSRO, she already explained how the measurement techniques, all those things. So in the GPSRO you have the GNSS satellite in the medium Earth orbit, and you have the LEO satellite in the low Earth orbit. So that's what we have, the two satellites. So the GNSS satellite, it sends the signal, and how much delay it is getting in receiving the signal at the LEO satellite. So the delay, that Doppler shift we measure, and from that either the refractivity or the bending angle, that is what we measure or we assimilate in the system. So if you see, this is the GNSS RO data we receive at NCMRWF. So this is from different actually whatever the satellite here mentioned, it is all those satellites in the LEO. The GNSS constellation is different. So GNSS constellation, US is having constellation, Europe is having, then Russia is having, China is having, Japan is having. So there are many GNSS constellations. So depending on the LEO, if the LEO is able to receive that data from different constellation, then it receives, and that type of data. So if you see, the GNSS satellite is here and the LEO is here, and whether it is means ascending or descending, whether the LEO is moving up or down, depending on that the signals are coming and we get the profile. So that is how the GNSS RO profiles are coming. So because this is not stationary, so the satellite is also moving. So it is like ascending or descending kind of thing it is coming. So depending on that, at this position the satellite is seeing here, at some other positions the satellite may be here, then the bending or the refractivity is coming from different portion of the atmosphere, then we get the profile. And this also we did the assimilation in our system, and what we found, like already Fiona explained, this is a sort of anchor observation, because this observation can help to correct the biases in the satellite radiations, satellite radiances, whatever we are assimilating. Because if you see, this is the direct measurement, we are assimilating either the refractivity or the bending angle. So the bending angle means it's not depending on the temperature or humidity or the atmospheric parameters present at that. It is how much bending it is happening due to the changes in the refractivity, refractive index. So that this is a sort of direct observation, and most of the radiance RO data we are receiving at NCMRWF, the rejection percentage is very less. If you are getting 100%, 100 observation out of 100, most 90 observations we are getting assimilating in this system compared to the satellite radiances. So this type of observation along with radio sonde observation we are calling as anchor observations. So this can help in bias correcting the satellite radiance data and other observations. So next, this is the this being said that these are the data that we are receiving at NCMRW. So this is the percentage of observation we are receiving, different types of data. So you can see that what are the different types of category, and this is the percentage of observation assimilated. So if you see that we are assimilating a very small amount of radiance observation, because we are assimilating around 10% or 15% of radiance observation. It is not because the radiance observation, whatever we are rejecting, these are of bad quality. It is because of the constraints in the data assimilation system. Because as she already mentioned that whatever the R matrix, you know that now the Jacobian, I am not showing the equation. So the Jacobian, if you are seeing, there are two terms. One is the, which term? Background term, and another one is the observation term. So we have the two terms, one from the model and one from the observation. So then we have to see how much the background error and the observation error it is coming, and you already know that B matrix and R matrix, the dimension, that what is the dimension, it is multi-dimension, that whatever N, M you are telling, the dimension is very big. It's not like 1, 2, 3 like that. So in that R matrix, if you see whatever we are using, that we are using the diagonal values only, we are not using the full matrix. So what we are assuming that there is no spatial correlation, there is no temporal correlation between the observations, but it is not like that. So suppose for example the INSAT 3D sounder data, so it is 10 kilometer spacing. So every 10 kilometer we are supposed to have the INSAT 3D data at 19 channels. So if you want to assimilate all this data, we have to give what is the spatial correlation between the two channels, what is the temporal correlation between the two observations. So but those information we are not giving in the R matrix. So whatever we are giving, so we don't have any upper diagonal elements or the lower diagonal elements, we have only the diagonal elements. So we are assuming that there is no cross channel correlation. So in that case, we have to thin down the observation. So in the operational assimilation, we are thinning the observation. So the thinning depending on the data assimilation resolution. So even if I told that we are running the model at 12 kilometer resolution, but our data assimilation resolution is even coarser. So we are not assimilating the data at 12 kilometer resolution because of the computational expenses. So we are assimilating the data at 25 kilometer resolution, 40 kilometer resolution. So if you have the 10 kilometer data, every grid point, or that every 10 kilometer if you are having the data, and if your data assimilation is at 25 kilometer, you cannot assimilate the 10 kilometer, means the observation is very dense and it is highly spatially and temporally correlated. So then we have to thin down that observation. So thinning is one important thing that we apply at the operational setup. So in the thinning, due to the thinning, that many of the observation, it's not bad quality observation, many of the good quality observations are rejected. So now we are developing systems that the currently available observation, means we are going for new and new observation, but we are not using the full, that 100% of the currently available observation because of the data assimilation constraints. So now our aim is to first use the full 100% of the currently available observation to change the data assimilation. It's not changing the technique, that how we consider or how we treat the observation in the system. So we have to use the full R matrix, like that we have to use. Then in that way the computational expense also more. So because that if you see that the radiance data assimilation, 100 data we are getting, we are assimilating only 10 to 15 data. So this is one of the constraints of the data assimilation system, because we have to do the thinning. So we do the thinning of the data, and most of the data in that thinning process, it is getting rejected. Okay, so then sir was asking what is the impact of each observation in the assimilation system. So this is one technique that forecasts sensitivity to observation impact. So that this is the global scenario, not over the Indian region. So as I explain, means we already discussed that we are assimilating different types of observation. If you see ERC, ETOS, CRIS, these are the instrument, whether it is conventional or satellite. So you can see the first one, impact per day, and the impact per observation, and the observation count per day. So if you see ERC, as we discussed that ERC is an instrument on board METOP series of satellite, and right now we have two instruments, two ARC instruments. And if you see that maximum impact is coming from either ERC or ETOS. And ETOS, we have, ETOS is on board some 4 or 5 satellites. So the maximum impact is from ERC and ETOS. And if you see the impact per observation is less, but we are getting more observation from these instruments, because it is multiple instrument on board different satellites. And if you see the CRIS also, so ERC, CRIS, these are hyperspectral, they are having thousands of channel, and ETOS, it is 3 instruments. And right now the HIRS, the infrared instrument, we are not assimilating, we are assimilating only the microwave. So then satellite, wind, aircraft, TEM, SINOP, like that it is coming. And if you see the ground GPS, the impact is very less. If you, that Fiona already showed the coverage of the ground GPS, the total zenith delay, the impact is very small, but if you see the impact per observation, it is having more impact in the assimilation system. So what it is showing, shown here is the how much these type of observation is helping in reducing the error in 24-hour forecast. So then we have to see which type of observation is important, and accordingly we have to devise the observing system. So this is, if you see the temp is the radius on the observation. So it is having 7.7% impact per day. And if you see the impact per observation, it is something, here negative means negative, it is that it is reducing the error, that's why it is coming in negative. And we have a lot of observation also. So some of the conventional observation and some of the satellite observation that are very important, if it is more in number, that error reduction is huge. So then accordingly we have to see these type of OIC, observing system experiment, and forecast sensitivity to observation impact, and we have to design, devise more new observing system, or which one is having more impact in the observing forecast. So ground GPS, again already Fiona mentioned, that is a set of data which is having lot of error. So the bias correction is very important for this type of data. So then after bias correction, so we have to spend lot of time and effort on bias correcting the ground GPS data, because again that zenith we have to off zenith, and zenith we have to correct that one. So this is no, actually this impact per observation. So each observation, if you see the impact per observation, we are having more impact from ground GPS, but we don't have many observation. The observations are very sparse. So if you have more ground GPS observation, the impact will be more. Then impact per day will also increase. So again it is depending on count. You see here the impact per day, impact per observation is very less, but the impact is more because of more observations. That's what it depends on. It is additive kind of thing. It's adding the information. Yes. Reducing. No, actually this one, it is reducing the error in the 24-hour forecast. So in this one, if you see impact per observation, it is minus 8% error reduction in the forecast. Like that it is coming. So it is little bit confusing. So the since it is error reduction, that we are showing in the negative. So each observation, how much it is contributing to the reducing the error in the 24-hour forecast. That's what it is shown here. So again, if you have more good quality observation, then it is playing more role, like YASI, ETOS, CRIS, satellite, wind, aircraft, TEMP, all those things. So then if you see the insert 3D imager, that we are assimilating only one channel, water vapor channel. So then the impact is very less. So now we are doing some experiment with the similar channels from other geostationary also. And coming to the Indian satellite, I hope I have time. Okay, okay. Okay, so coming to the Indian satellite data, so mostly if you see almost all the operational centers, they use all the means global data, and at NCMRWF, we are the first to use all the Indian satellite data and demonstrate the quality is good, and then the other centers, they start to use the data. So starting from Kalpana, so the first dedicated meteorological satellite by ISRO is the Kalpana. So from Kalpana, we assimilated only the AMVs. We didn't use any radiance data. So we showed that again it is a collaborative work between IMD, NCMRWF and ISRO. So ISRO provided the data and we validated and what is the error in that data. So many iterations, and then the quality of the data is improved. Then comes the OceanSat 2. So OceanSat 2 also, if you see the scatterometer data, so this is one of the best scatterometer data similar to the QuickScat, and we did the assimilation and operationally also. And next is the INSAT 3D data, so that we assimilated both imager and the sounder data and AMVs also. So these are the data. So if you see the imager and sounder assimilation, we didn't find much impact in the system, but from the AMVs. So as she already explained the technique how to derive the AMVs. So in the NCMRWF assimilation system, from the IR instruments, we are assimilating the CSBT, that is the cloud clear sky brightness temperature. We are not assimilating any cloudy information from the IR. So in the case of IR instrument, if you see in the INSAT 3D radiances, imager and sounder we are assimilating only under the clear sky condition. But AMVs, how they are deriving? They are tracing the, there are traces, either it is cloud or the water vapor. So the cloud information we are getting from the AMVs. So when we assimilate this imager and sounder data along with AMVs, that both the clear sky condition and the cloudy conditions are coming, and their complementarity is coming, so that we have to assimilate all these things together, then only we get the desired impact. Then comes the megatropics. So megatropics is one of the best satellite that is by Indo-French, that collaboration mission, and we have the instrument Saphir. Saphir is the one of the means very good instrument in the microwave region of the spectrum. So again she showed that spectrum, that 183 gigahertz. So 183 gigahertz we have the water vapor absorption. So there that lowest peaking is there, so that all the Saphir channels are in the 183 gigahertz region. And again there was another instrument ROSA, that is the radio occultation in the Saphir. So that also we used extensively in our operational system. Then comes the SCATSAT. SCATSAT again it is the scatterometer vision, and inside 3D are AMVs, and sounder and imager also we used. Then we have the OceanSat 3. This is the latest scatterometer mission. We are using that data, and microsat 2b, it is the continuous, it is the successor to the megatropics Saphir, and we are using those data in our assimilation system. These are some of the example how we use the megatropics Saphir data. So you see there are three instruments like one Madras, then Saphir and Skyrab. Madras is an imager, but unfortunately Madras didn't work properly. So after 2 months post launch, that instrument failed. But we the ISRO and CNES, they designed this instrument in such a way that there is a synergy between the imager and sounder, Madras imager and Saphir sounder. But we could not use both the things together, but we used the Saphir. And this Skyrab is the radiation budget. It is not for assimilation, only for the tropical that radiation budget. So if you see, when we compare the weighting function, she already explained what is weighting function. So there we compared the weighting functions of MHS, Saphir and ATMS. So what we are getting, the lowest peaking channel of Saphir, that is not there in other instruments. So the particular the main important of Saphir is the lowest peaking channel of Saphir, and we got most impact from the lowest peaking channel of Saphir. And all these things, if you see, it is in the 183 gigahertz of the spectrum where the water vapor absorption is happening. So then we did some experiment. We have to demonstrate that because the Madras and Saphir, the sounder and imager, the synergy we could not use. So we did some experiment with imager sounder together. So the AMSRE, and what we found was, when we assimilate the imager and sounder together, the impact is the maximum. So in the lower level we get the maximum. This is the super instrument, if you see the super instrument. So we are getting this is the error standard deviation. You can see that very less standard deviation. So it is coming, the synergy between the imager and the sounder, it is coming. And this we informed ISRO also, and we requested ISRO for the megatropics repeat kind of thing, because it is one of the best instrument used by many of the operational centers. And here also you can see the Saphir impact. So Saphir, it is a single instrument from one satellite. So it helped to reduce around 3.5% error reduction in the 24-hour forecast during 2018. So if you see when the instrument deteriorates, that it was not means working properly, 2019, 20 and 21, the impact was very less. So from the single instrument, if you are getting 3.5% error reduction in the forecast, means it is very good. So that means this type of instruments are very important for assimilation. So similarly, this is the microsat 2B. It is the next one experimental mission, and it is similar to Saphir channels if you see. And we did that similar experiment, and what we found is the impact is similar to Saphir in the assimilation system. So the humidity and analysis increment, the humidity and temperature, it is almost similar we are getting. So this is again inside 3D, 3DR sounder. So something whatever we did, so what we are assimilating only the water vapor channel because it is peaking high in the atmosphere. This is the weighting function. And other channel, if you see, there is not much, it's not much that information in the vertical. So basically we assimilate only the water vapor channel. And what we found is, as I already told, that it is the clear sky assimilation, and we assimilate the AMVs from the cloudy atmosphere and from the water vapor. So we get the complementarity of AMVs and water vapor channel radiance above 500 HPA when we assimilate these things together. That's what, we are assimilating the radiances in the clear sky, and at the same time we are assimilating the AMVs, the atmospheric motion vectors. So atmospheric motion vectors we are deriving from the cloud tracers. So she already told that one box 24 by 24 pixel, you are seeing in the first 15 minutes one image, movement of that one, so that the cloud movement, how it is moving. So from that we are deriving the wind speed and wind direction. Similarly in the water vapor, so we have the clear that water vapor, clear sky water vapor AMV and cloudy water vapor AMV. So water vapor tracer also we can do that same way, we can trace and we can derive the AMVs. So from AMVs we get the cloud information, and from the clear sky, if the cloud atmosphere is clear, there is no AMV because there is no tracer. So we should have some tracer to derive the AMV. So that's what we are assimilating, the clear sky radiance and the AMVs together. So both are complementing and we are getting the best impact. So then the AMVs also, if you see, we did lot of experiment that AMV quality is on par with the data over the data from the Meteosat, and we could see the impact in the cyclone simulation, all those things. And coming to the scatterometer also we did, since we are using the 4D VAR, so the scatterometer, it is 10-meter wind. Since the 4D VAR, the background error matrix is there, so vertical correlation it is coming. So we can see the impact in the vertical also, even if we are assimilating only at 10 meter. So this is the latest one, the OceanSat data. So if you see, this is the 1 day coverage. If you see that we are getting the data at NCMRWF, and this is we validated against the buoy observation, because before using any new type of observation we have to validate the data against the available in situ observation. And what we found is the wind speed error is less than 2 meter per second and the wind direction error is less than 20 degree. That is the mission goal, and the validation also showing the same thing, and we started assimilating the data in our system. And when we come to the gap areas, so this is the that satellite equator crossing time. So this is mainly, we have shown here only the microwave satellites. So if you see that we are telling that we are assimilation 6 hourly intermittent assimilation. So 0, 6, 12 and 18. So we have many satellites equator crossing time during the 0 UTC and 12 UTC, but we don't have much during the 6 and 18 UTC. It is over the Indian Ocean region. So Indian Ocean region we have a gap during 6 and 18 assimilation cycle. And whatever these dotted line, it is showing that these satellite that lifetime may end very quickly. So these satellites may also not be available in near future kind of thing. So these are some gap areas if you see in the satellite data. So we need to have more satellite with equator crossing time around, I mean, maybe 11:30, like 23:30, like that. So these are some of the gap area. And similarly, if you see the gap area in the scatterometer thing. So if you see the currently available 3 scatterometer, OceanSat 3, SCAT B and SCAT C, we don't have much data over the Indian Ocean region during 0 UTC. But we have data during 6 UTC, and even 12 UTC we don't have data, and 18 UTC we have some data. So that also some gap area, and mostly at NCMRWF we give the forecast based on either 0 UTC initial condition or 12 UTC initial condition. And during these two initial condition, we don't have much data over the Indian Ocean region, particularly if there is a cyclone. So this is another gap area. So we need some scatterometer mission in the afternoon orbit also, so that we get more data. So I will stop here.
Questions?
Yes, sir.
No, and this is about the thinning of the data. Suppose maybe at a particular time, at a particular place, maybe there are more than one observation of a particular parameter. So, or maybe they both of them passes the quality control. So, which data that
No,
model
actually we do the thinning mainly for the satellite data, not for the conventional data. Conventional data we do some other check like that, hydrostatic check, buddy check like that, and if it is passing the quality control, then we do assimilate. The thinning is mainly in the aircraft data and the satellite data, and we do the thinning with respect to the satellite, not with respect to other satellite, like that we do.
Okay. And madam, about that denial of that, you told that reduce on the data that quality is not good like that. Suppose means we are giving some value of the some parameter to the model, but how the model is understanding that that value is not good or bad, just comparing with the background.
Yeah, actually, yes, we are comparing actually for the NWP person. What is the best? The best is the first guess. So because we have the information at each and every grid point. So that is the best, the complete information. So whatever the data is coming, we are comparing with the background. So if the data is, suppose the temperature or the humidity, whatever it is coming, we are comparing with that O minus B, that background innovation is coming. And for particular type of observation at particular level, we have given some predefined values. The O minus B should be less than this much. So if that value exceeds, then that type of, that particular data will be rejected from the assimilation system. And if you see the radio sound data, we are giving the profile. We have observation from 1000 HPA to 10 HPA. So it's not like that if one observation at a particular level is bad, we reject all the data. It's not like that. Level by level we are doing the quality control. If the particular level observation, say 500 HPA, the temperature is not good, then we reject only at 500 HPA, not the whole profile.
Thank you.
So it is again depending on the O minus B value.
Ma'am, you have told that recently in your forecasting system you have used OceanSat 3 data. So you are comparing with buoy observations, but buoy observations are quite sparse. So
It is sparse. We collocate that one. So we have to take the temporal and spatial thing. So means temporally within half an hour, if it is 30 minutes, and spatially within maybe 10 kilometer. But we use some coarser the spatial thing around 50 kilometer. So if the scatterometer value and the buoy observation, it is within 30 minutes interval and within 50 kilometer, that spatial resolution, we considered that particular observation for collocation, validation.
okay, so means
So it is very less number of observations.
so for means a temporal, I got a temporal resolution for suppose 3 or 6 months, like that data you have compared Means
we compared for whole year.
whole year.
One
okay.
year we compared how much it is coming. So we got some less. Suppose if we are comparing with the background, we get every observation we get the value. But for the in situ observation like buoy, as you told that it is very sparse. We don't have many observation over the southern hemisphere also. So whatever is available and that is in the collocation with coming under the collocation criteria, that only we considered.
Okay. And impact per observation, suppose in one particular location, means impact per observation from, suppose we have observation from two different sources. So if impact per observation from one source is higher, so do we means take that observation itself, or do we average out both
No,
the observation?
what do you mean by particular site?
Means
It is a particular.
suppose in a particular location we have data for winds from ocean, suppose from a scatterometer as well as some other source. Then suppose impact per observation for scatterometer is higher than the other source. So at that location will we average out both
No,
those?
no. Actually, if you see scatterometer, it is only over ocean. It is 10-meter wind. And we don't have much observation at 10-meter wind. And suppose if you have at the same location, you are having AMV, but that AMV is at different location. So then the impact per observation of different types, it is different. So if it is coming at the same location, then we do the buddy check, which one is correct. Then accordingly in the assimilation system itself, we reject. So which one is more closer to the background, that only we will take. Like SYNOP, AWS means METAR. These are three types of surface observation. So we do the checking of these three things together. And we check whether the SYNOP at the particular location and the AWS and the METAR, are they matching? So if they are not matching, and which one is more closer to the that observation background field, that we take. And again, if those three are matching, and we will see what is the observing time, because we are doing the 4D VAR, we can take in account of the time also. So whichever is more closest to the that background time, that assimilation window, that only we take. That.
Can you please explain a little bit about analysis increment, which plots 3 or 4 plots?
Analysis increment, that means that you have that seen the Jacobian equation. So whatever it is coming, so you have the background term, x term and xa and xb you are having. So we have to do lot of means iterations, like Fiona told that we have to do means it is like 6 hourly assimilation cycle. So we are taking from 21 UTC to next 3 UTC. So that means 6 hour it is there. So our background also we are having the 6 hour forecast. So then each iteration at our center we are doing some sort of 90 iterations. So each iteration we check with the background and compare, and whether it is matching, it is converging or not, then at which iteration it is converging, that value we take. So we have the background value, and the after the last convergence we get the assimilation. The assimilated field, suppose if it is temperature, so the temperature from the assimilation, that analysis we get, and we have the background also. So then we have to, actually if we speak the analysis increment is the difference between the background and analysis. It's not, it's overall it is correct, but the whatever the observation we are assimilating, suppose we are assimilating some observation in the polar region, that also may have some influence over the tropics. So all the observation, what is the impact of all the observation in the background, how the background is changed, all those changes are considered in the analysis increment. So then we see the analysis increment, if you field, if you see, it is very small, but that small increment, it makes lot of changes in the initial condition. So it's not like I am assimilating one observation at Bangalore, that influence is only at Bangalore. It is not like that. It can influence more region. So if you do the single observation experiment, and you might have heard about the Lorentz model, that butterfly effect, all those things. So it can affect more region. So that way, what is the impact of all observations, all type of observation assimilated in the system on the background? That is the analysis increment. What changes it has made? That is the analysis increment. Maybe in that we can tell it is the difference between the final analysis and the background field, initial background field, how much changes you are seeing. No, actually that is very important. As per the WMO criteria, when we install any instrument, that they means whoever is installing that instrument, they have to follow the conditions. It should be in the open space, there should not be any pond or there should not be any trees like that. So if that local effect is coming, means model cannot include all those things. So then all the meteorological center, when they install the instrument, they should follow the WMO criteria. That is very important. That's why if you see that we have given for 2-meter temperature, 2-meter humidity, this much error from the background. So if it is exceeding this much error, it won't go into the assimilation. So there is, if you see that the assimilation system, we are doing the assimilation for improving the initial condition. But sometimes the assimilation system can also assimilate the wrong information. So maybe the information is that whatever the local data it is coming, that is wrong, but it is the O minus B, when it is checking, it is passing the quality control, that information can go into the assimilation system. That is one of the drawback of the data assimilation system. And sometimes the good observation, like we are doing our model at 12-kilometer resolution, but something is happening at sub-grid scale kind of thing, maybe within 1 kilometer or 500 meter, that information we cannot assimilate in the system. So that also, these are some of the drawbacks of the data assimilation system. But for changing these drawbacks, we need to invest more computation, more whatever the R matrix, B matrix we are telling, we have to include that the full matrix instead of the diagonal matrix. So those type of works are going on, but it will take some more time to establish that one. So the instrument, that quality, that is also very important, and where we are putting the instrument, especially the surface. Yes. Huh. It's not on.
Now I'm
Okay.
suppose we have a satellite data. So could you please give me an explanation of how to do bias correction, quality control, selection of channels to incorporate into DA?
Okay. So you have, suppose if you are taking the INSAT 3D. So INSAT 3D imager, if you are taking, you are that is the 6-channel imager. So one channel in the visible. So right now we are not assimilating any visible reflectance. So that channel we cannot assimilate, and the second channel is coming in the shortwave infrared, that is also like visible. So the first 2 channel we are not assimilating. Understood? So because it is depending on the frequency. So here in our system right now we are assimilating only the radiance, not the reflectance. The first 2 channel then we cannot consider. The third channel, it is the middle wave infrared. So middle wave infrared, what information we are getting? So whether it is the atmospheric information or surface information, like that we have to consider. So from the middle wave information, whatever we are getting is the column integrated information. So it won't help the data assimilation. And we have the water vapor channel, it is peaking around 400 or 500 HPA. So we get the water vapor information or the water vapor absorption at that particular level. So we need that information for the humidity improvement or the whatever the moisture improvement in the initial condition. So in that way we select that water vapor channel. And other 2 channels are the window channels, that is TIR, the thermal infrared 1 and 2. So that also we can assimilate at the higher level, but we cannot assimilate that in all surface, because if you assimilate over land, then that land, if you see over ocean and land, ocean we can say it is a homogeneous surface, but land is not homogeneous. So we have to see the surface homogeneity also. But water vapor channel, if you see, if it is peaking high, so most of the information is getting to the satellite either from 400 to 500 HPA. So below that, the satellite is not seeing from that particular channel. So we can assume that in that particular channel there is no impact from the land. Surface impact is not coming. So otherwise what you have to do, we have to assimilate all surface, all sky condition. But right now we are not assimilating all surface, we are not assimilating all sky for IR channels. So in that case, that whatever the limitations are there, if we can assimilate over land for the TIR 1 and TIR 2. So for that you have to see where the channel information is coming. So what the satellite is seeing from that particular channel, that we have to see. For example, the Saphir we are having the 6 channel. So 6 channel, I think if you see that weighting functions, this is for insert 3D, if you see the weighting function. So this means we are not getting much information from this one, because this is very sensitive to that surface. So these things, these channel we are not assimilating, but only this channel where it is peaking high in the, I don't know what sign out it is coming. So from that insert 3D imager, we are using only this one, and if you see for the Saphir, see, this is the Saphir channels. It peaks at different regions of the atmosphere. So this is the pressure, if you see. So the lowest peaking channel, it is peaking around 700. So you can see the peak, you know the weighting function. So like Fiona already explained that weighting function. If you see the weighting function shape, now from where, from which part of the atmosphere the satellite is seeing most information. So for this particular, actually the satellite is seeing the integral information, but most of the information is coming from this particular region of the spectrum. So for the microwave, if you see, almost all the Saphir channels are peaking above 700 HPA. There is no surface impact is coming. So we can use all these channels in the assimilation. But if you see here for MHS, some of the channels are surface sensitive. So these channels we are not assimilating. So right now the surface sensitive channels we are not assimilating, but works are going on to assimilate all surface, that like all over land, sea ice, then snow, all those things it is going on. So likewise we can select the channel. So you have to see the channels like that, where what information it is relevant to the NWP, where it peaks and what information we are getting. So there is one site, I think that is WMO Oscar. So you can see that site, and each instrument details you can see, and there you can find what information from that particular channel you are getting, whether it is what is the absorbing gas there, where it is carbon dioxide, where it is water vapor, what type, or ozone, what type of absorbing gas is there, and what type of information it is giving. For this one, all these are humidity channels. It is giving you all humidity information at different level. Similarly, if you see AMSUB, it is giving temperature information at different level. So depending on that, we have to see which is what information, depending on the frequency, what is the absorbing molecule in that particular region, and what information we are getting, whether it is ozone, whether it is humidity or temperature, all those things. No, there is no limitation.
Then why we are not?
No, actually for microwave we are assimilating all sky, because microwave it can penetrate through the cloud also. So again for assimilation, the brightness, temperature or radiance we are telling, we don't have this radiance or brightness temperature in our Jacobian or equation, in our assimilation equation. What we are having in that equation is only the geophysical variables that is in the model, temperature, humidity, wind, those things. But we don't have the brightness temperature. So if you want to assimilate the brightness temperature, we have to introduce an observation operator. So that observation operator, it calculates the equivalent of the brightness temperature from the model parameters and compares with the observation. Then the O minus B, all those checks are coming like that. So for the IR radiation, whatever the cloud, it cannot penetrate through the cloud. Whatever the satellites, if there is a cloud in between, the satellite doesn't see the information below the cloud. So it is very difficult to assign where is the cloud top or cloud base. It is very difficult. So in that case, we have to assume the cloud, and that cloud base, cloud top is at this particular level, and the information is above only. That means we are doing something like gray scale, gray cloud concept kind of thing, but we are not getting much impact from that one. So that's why we are not assimilating the all sky infrared, but we are assimilating all sky microwave. So for that, like Fiona already told, we have to compute all the hydrometeors also, because it is scattering. So that scattering part also we have to take. So in that observation operator, we have to include the scattering also. Okay. Yes. Actually, that solar intrusion you are talking, no? So that solar intrusion time, we are not assimilating that one. So we have that from 15 UTC to around 3 UTC, we are not assimilating the data. So that time window, we are rejecting all the data from assimilation. Surface channels, we are not assimilating. We are assimilating only the high peaking channel from inside 3D sounder. Because we already talked to SAC, Space Application Center. So in the insert 3DS, I think they are planning to reduce the sun glint problem. So if they reduce that one, then we can increase our assimilation thing. Otherwise, we have to reject the data in that particular assimilation window. 3 UTC. But we assimilate AMVs because they do the retrievals, the correction, everything. So AMVs we assimilate. Okay. No other questions?
Just one clarification.
Okay, sir.
This Aeolus Doppler grid profile. What is its vertical resolution?
Vertical resolution, sir, for me cloudy, it is a high resolution we are getting. But for Raleigh, it is coarse resolution. I need to check what exactly the resolution.
It will be much more compared with the
Yeah, yeah, AMVs. Because it is profile.
So AMV is typically lower atmosphere, upper atmosphere?
No, upper atmosphere. Actually, AMVs low level, mid level, high level. We are having at every level depending on the cloud. And above 400 HPA, we are having the water vapor winds.
So when is 40 bar operational with this?
It is, I think it is in 2009 onwards, we are running the 40 var. And in 2013-14, we changed to hybrid 40 var. Using the background error means covariance from the ensemble system.
Hybrid is better?
Hybrid is better. Because otherwise we are using that climatological background error that is constant. So the flow dependency is not coming in the background error. So when we introduce that 30% of error covariance from the ensemble, that flow dependency is coming. It's not much improvement, but there is a slight improvement compared to the 4D one.
So let us thank Dr. Indira.